Hello everyone and welcome to a new episode of All Things IDA. In this episode, I'm going to be covering briefly how API hooking works, in particular how the Microsoft DETOUR'S library work, and then we will be using IDA Debugger with the WinDBG Debugger plugin to automatically detect hooks in a running process or in a crash dump. Let's get started. So to get started, I'm going to clone this simple project. This is just a CMake solution. And I already set up the build folder and configured CMake. And I have the solution open in front of me. To use detours is really simple. We have to begin a transaction, attach the hook, and commit the transaction. And like this, after we commit, the API in question will be hooked. So here we're hooking the beep API. So we take, before starting the hook, all we do is we take the pointer to the API and we assign it to a variable. And that will be our trampoline. I will show you what the trampoline looks like when we attach IDA. And then once we attach, we also specify our replacement hook. So the actual API will now be redirected to our API. And if we choose to call the original API at any time from the hook, then all we have to do is call through the trampoline. And then anybody using the hooked function will be redirected to our implementation and so on. And then later, if you want to remove the hook, we also open transaction and simply detach. We pass the trampoline and our hook, and detours will undo the hooks. So let me start tracing this program. Just all the way until before I actually hook it. And so we're gonna attach IDA and take a look at the process before the hook. So running IDA. By the way, this is a 32-bit process for now. It won't make any difference. I'm going to start with no database and choose the WinDebug Debugger plugin. And then in the options, specific options, I'm going to select non-invasive user modes attach. This will allow me to attach even though we are already debugging and attaching. So that's a good way to inspect the running process, especially if it's already being debugged. I don't have to do this. I could have run without a debugger and do regular debugger attachment. But just to illustrate the non-invasive attach. Okay, so now we should have the list of processes, and I'm gonna select, find the process called simple, and attach. And here we are suspended exactly at the same point where we are in the IDE. So let's just simply load the PDB files for this. And at this point here, we're gonna be getting the detour attach. But let's just go to kernel 32 beep and take a look how it looks like. So let's also show the opcodes. And here we have those 2 bytes. These are for the HOTPATCH, where one could simply do a small, short negative jump up here, for example, to HOTPATCH this API. Okay, so as we can see, the beep function is as is, no hooks, no nothing yet. So once we go to beep, we see the original code. Great. Now let me detach the debugger so we can continue single stepping Visual Studio. Okay, minimize IDA. And now we're gonna step over the attach and the commit. Attach will not directly do anything yet. It will set up the trampoline and so on, but it will not really touch the API yet. After we commit, now we are in the hook. We are hooked. We hooked the beep. Now let me attach again. No need to readjust the debugger settings, but just to double check, we can always verify that it's still saying non-invasive user debug, user attach. So let's attach again and select as well the same process. And at this time, Here, for example, this is source level debugging in IDA. Let's go back to the beep function directly in kernel 32 and see what happens to the code compared to the previous case. So if you observe, this time the body of this function is replaced with a relative jump to my implementation in my source code. So this my beep, this is basically, if we go to kernel, it will jump to this, which is exactly this code. So this code, what it does, it will do simply print and call the original API through the trampoline. So what's a trampoline? Just the name, which means it's just a landing zone where when we put the hook here, we did override the original bytes. And by doing that, how can we re-execute the original API? Well, we have to execute the copied instructions first and then continue execution after the hook. So here, if we make code, we should see the continuation of the kernel function beep, but the first few bytes have been changed to jump to our hook. So here, this is the actual continuation of the body of beep. So let's inspect the trampoline. In the trampoline, we should expect the HOTPATCH bytes and part of the prologue, and then a jump to this point. And actually, once we reveal that, we should see a cross-reference here, which we don't observe as of yet. So let's follow it. And here it's calling the trampoline. So the trampoline is created in an allocated memory, executable memory. So that's the pointer. This is the real beep global variable in my source code. That will point to the trampoline. So this here is the trampoline. If we inspect the section, this is a debug segment. So it's allocated by DETOUR'S library. It's read execute. After we commit, the right bit is removed and it remains read execute. So we can safely make code. If we make code here at the trampoline start, we should see the copied bytes and then a jump to the continuation in the original function. So pressing C here, we can see this is the HOTPATCH bytes. This is part of the prologue, and then jump to the continuation. And now that's the cross-reference from the trampoline itself. So this is how hooks work when we use either DETOUR'S or some other hooking libraries. The concept remains the same. Usually they hook at the beginning. Now, just a few ideas. It doesn't have to be always replacing at the beginning. It doesn't have to be a relative jump at the beginning. It could be any form of ways to redirect the execution from the beginning of the function to the hook. So some malware or some software wanting to avoid being detected as hooks, they don't directly use jumps. They might, for example, use move registers and push and return, or push directly the offset and return. So you can do all sorts of things, then jump to the hook, just to evade the detections, basically. So let's detach. And let's put a breakpoint here. And one more here. So let's run it. And here now we display the message that we intercepted the API. And then we're gonna call the trampoline. If I switch to assembly view in Visual Studio and single step, it's going to go through the trampoline, the same stuff we've seen in IDA. This is part of the trampoline. And then it's gonna jump back to kernel 32 continuation. So now here, this is the beginning of the beep function that jumps to the hook, but we jump past the hook to continue the function. And here we go. We executed it. Now, same story. If I detach, everything is reverted and so on. All right. So this covers the basics of the hook, how to hook. Now what I'm going to do next is do massive hooks using another example in the DETOUR'S API. Take a memory crash dump and work on a scenario where we have a crash dump. How can we detect which functions are hooked? Okay, so I'm gonna stop debugging here. We're done with that example. In the same package that I downloaded, there are a bunch of binaries I can use. So I'm gonna use okay, let's build release. And then generate a crash dump of some process. So I'm gonna run Hue. Let's see where's Hue. Okay, that's Hue. We're gonna instrument it using one of the examples that come with DETOUR'S. Take a crash dump and then show you how we can detect all the hooks. Okay, so now let's go to the bin release and say with DLL. We're gonna use this utility that comes with DETOUR'S. We're gonna use the trace API.dll example. And the process is Hue itself. But before I do that, let me also run DETOUR'S give us a nice logger. So let's run that logger so we can see what's happening. Okay. Let's run. And that's Hue. And here we have all the stuff that are being intercepted. So we can safely assume that Hue is fully hooked. Most of the APIs in the trace API DLL have been installed. So here, as I use Hue, everything is being intercepted. So now let's take a crash dump and assume that we started with a crash dump. For this, I'm gonna take a crash dump using the 32-bit task manager, since I'm gonna be working with a 32-bit program. So I explicitly run the task manager from syswow64. Let's go to Hue and create crash dump. Okay, so this is now what we're gonna continue working with. So let's go to temp dmp and paste this one. I don't need the logger anymore, and we should be good to go. Okay, now assume we have this crash dump. Somebody asks us, hey, let's see what are the hooked APIs in that crash dump. So just a quick inspection. So I run IDA. I'm running IDA32. As usual, we've seen this scenario before, opening a crash dump, but this time we're gonna be looking for hooks. And it's useful to use WinDebug because it has such built-in functionality. So as IDA loads, let's give it some time to load the symbols. And meanwhile, I'm going to explain what we're going to be doing. So I opened the install WinDebug just to open the help file real quick. And I'm going to be using the for each module. And for each module lets us basically work with, for every module, we can issue a command. And within the command, we can substitute stuff, for example, module name and so on. So we're gonna use the for each, and then we're gonna also use the built-in extension called check image. So check image, we can give it a module and some options. For example, first let's just run check image on a single module, and then we're gonna combine that with for each. Okay, so now we are inside the crash dump. We can do the usual stuff. For example, I switch to the WinDebug CLI. We can type, for example, loaded modules, etc. So let's take user32, for example, and show you the check image. So check image -d. I'm gonna use the simple output. You can use different options, but I'm just gonna use the -d just for summary. And let's see. So when we do that, uh, that extension itself, check image, is gonna detect basically corruption in the images by comparing them to the ones in the symbol store. So it will find the original ones non-patched, match the DLL version, try to get the original binary from the symbol store, and compare the bytes. So that's a logical thing to do actually. And from the output here, we detected so many errors, and those errors basically designate the discrepancy between what we see in memory versus what the original DLL should look like. So that's an indication of patching. Whether it's hooks or not, this is an indication of patching. Now we can directly tell if it's a hook or not from, so this is the output, and if we double click on an address, the address coincides with the beginning of a function, set scroll position, set scroll range. And so if we follow it, you can see this is what we described earlier. This is just the hook, which will go to the hook itself, which will eventually call the original API through the trampoline. So we follow trampoline pointer, still inside trace API, that's just the pointer. This will take us to the location of the trampoline code. And in the trampoline code, we should see the stolen bytes. So if we were looking already WinDebug detected that the first bytes, that 5 bytes, original were these, and actually we can see them in the trampoline, minus of course this. This is the jump to the continuation. And what we observed at the function now is the hook. We can see the E9, but these are the original bytes, and actually these are the original bytes that the trampoline uses. So now if you want to detect the hooks for every module, we can combine check image with the for each module. So our command was check image minus d user 32, for example. We're not gonna do that. We're gonna say for each image, and we can go to the help again. For each module, and module check image minus d, and we need to just use that variable module name. So if I invoke this extension, pass this argument, it will be substituted for each module. Now when we execute a command from the CLI, IDA will not stream the output. That means IDA will execute the whole thing, wait for the output to be finalized, and then display. That's why we will see a large delay if it happens. So if you think IDA is hanging, it's not. It's just simply waiting for the whole thing to finish. All right, it finished. And now if we start scrolling for my commands, it will go after every DLL it finds. So kernel base, user 32, and every module that the for each module basically displayed can enumerate basically. So that's it for today. I hope you found this useful. The same things we explained applies to x64. No changes really. The concept remains the same. If you found this episode useful, please like and subscribe. Thank you.